Swayam Prabha. Digital India. Educated India.
Okay, so little bit more on this maneuverability. We wrote this expression this is elevator deflection required per g, right. Setting this 0 will give you what does it mean? Setting this 0 means you can get a large acceleration even without deflecting the elevator, right. So, elevator becomes very sensitive and any small deflection in elevator can give you large normal acceleration, right. That is what small of this quantity means, okay, and it is a function of the CG location, right. Cm alpha is a function of CG. So, CG location where this becomes 0 is the point which is called maneuver point, right. So, stick fixed we also have an expression for, so can you read this? Stick fixed maneuver point can be obtained by setting this derivative to 0 and finding the corresponding center of gravity location, right. If I want to find out stick free maneuver point, then what is the derivative that I have to set 0? Set this dfs over dn to 0, right. So, I will call this stick fixed maneuver point as x MP, and if you want to see how it is related to the neutral point, fixed stick fixed neutral point. So, clearly this is going to lie aft of the neutral point, because we said that CMQ is negative for positive damping in pitch, and this quantity is positive because CW is the weight coefficient, which is going to be very large, right. So, CW is very large as compared to this CLQ. Okay. So, this is where the location of the maneuver point is, and CG is here, right. So, I want to look at let us say what is happening to this elevator control requirement per G of normal acceleration with respect to the CG movement, right. CG can change, and that can be a design criteria, right. So, only few more things that I want to say about this. Right. So, my x axis is the CG location. Let us draw the right, and let us start moving the CG. Okay, we see how CG is going to change this control requirement with respect to velocities. So, I can plot this against this for different velocities. Okay. So, I am drawing it for 3 different velocities. Or let us say so, all of them actually pass through this point, okay, for different time speeds, and this V1, V2 and V3. V1 is less than V2 and V2 is less than V3. Right, you are flying your level trim when you want to initiate a maneuver, right, and velocity is a constant, right, in this maneuver, the maneuver that we are talking about, the pull up maneuver, right, from a level trim condition. Okay. So, this is how it looks like. There are few things that you can note down. Right, all the curves are passing through this point and that point is the maneuver point. So, it is independent of air speed. Right. As the airspeed is increased for a fixed CG location, you can see that elevator required has reduced, right. Moving forward means going towards the aircraft nose, right. Okay. So, when we are moving the CG up towards the neutral point, static margin is decreasing. What happens? Less stability, so I can maneuver better, right. Yes, so take any trim speed and you are moving your XCG towards X and P, right. So, this curve is coming closer to this 0 line, right. So, it's the elevator requirement is actually decreasing. Of course, with large transport aircraft you do not want to maneuver, right. No larger transport aircraft will actually maneuver. So, this will be what category of airplane? Yeah, fighter and
military transport.
no, military transport also. Yeah, right. What happens when CG crosses this maneuver point? Control reversal, right. So, now when you are taking your elevator up, or in this case to get the normal acceleration that is demanded, you have to put your elevator down, right. Of course, the aircraft also has become unstable, isn't it? You are crossing this x and p, so aircraft has become unstable, right, and this is what is happening. So, any acceleration that you want in normal direction, this sign of delta E will be changed, reversed, right, that is what it means. But normally you would not want to cross this x and p, right. What it's all telling you is that you have this margin which is the maneuver margin, right. So, you can, your aircraft can be marginally stable, no, it can lie very close to this x and p, or marginally unstable, when it is going to cross this x and p, it can still maneuver, and maneuver it will be stable, it can still have a stable maneuver, right. So, one of the ways to find the XMP in some other book is also by setting this to 0, but with the Q effect included, right. So, I would give you this as a problem for homework problem. Okay. So, try to see what is the relation between this and this. So, this DCM over DCL with pitch rate effect included, right. When you solve this for the CG location where this becomes 0 is equivalent of finding CG location through this relation, okay. And can somebody work this out? Try this out. So, this is how in Pamadi's book, this is how they are trying to find out the maneuver point, okay. And see if you get the same expression using the both relations. Okay. Here this CM includes the Q effect with respect to G maneuver, okay. And we are still talking about longitudinal dynamics, right, longitudinal plane. We have not talked about maneuver in any other plane other than the longitudinal plane. So, see if you get the same expression for XMP by solving this as what you get by solving this, right. Okay. So, we said we will solve some problems in this class, and let us so you have a general general aviation airplane with an aft tail. Okay. The weight of the airplane is this. Okay. So, I am converting all the units into SI units. Here they have given it in FPS units. All right. S W is wing planform area. Lift curve slope for the wing is 4.44 per radian. Zero lift angle of attack for the wing is minus 2.2 degrees. Wingspan horizontal tail area. So, it is given in feet square, trying to convert to SI units. Span of the horizontal tail. So, BT is okay. 3.6576, okay, roughly. CL alpha tail is 3.97 per radian. What is this term? Elevator effectiveness parameter, right? 0.6 LT is tail arm length, LW is wing arm length, right. So, CG location from the aerodynamic center of the wing is this LW, right, and LT is the aerodynamic center of the tail, the distance between aerodynamic center of the tail and the CG, right. Okay, let us see what all we want to find out. This aircraft has a trim condition, level flight trim condition, which is at alpha equal to 0. And this alpha is alpha of the airplane, right. So, fuselage reference line, and this we can obtain without changing the elevator. Okay, let us say there is a condition like that. And at this delta E0 there is no lift produced on the tail. Okay. So, all of them are trim values. Sea level condition. So, we will also assume that the aerodynamic centers of tail and wing are lying on the fuselage reference line. Okay. So, there is no moment created because of the vertical distance, and CG is also lying on the fuselage reference line. Okay. So, all that we are assuming, and the problem is to determine one location of gravity CG, the wing incidence angle and the tail incidence angle, right. Pitch stability derivative, and delta E versus V I think you are familiar with this one problem at least, right. It is not so difficult to solve this. So, I will quickly. So, you want to find out the location of center of gravity, and what is given is this. So, we have to solve lift equal to weight for trim condition, right. So, one condition is this, and second is that Cm Cg must be 0, right. What is L? L is right lift at the wing, and you have to add this tail part also. But here we are saying that we are flying a condition when alpha is 0 and delta E is also 0, and the lift produced at the tail is 0. Okay. So, that is given in the problem. So, you are setting this to 0. So, W is right of the wing. So, alpha is again 0 here, trim condition, and now I can find out what CL naught W is using this, isn't it? I know everything here, I know the weight, I know all these quantities. So, I can find out what CL naught W is, right. Is this all right? Okay. We also have to find out the downwash angles. So, the expression for that is let us try to solve this 2. Okay. What is 2? This Cm naught is the total Cm naught, right, plus or Cm naught tail is what? Plus AT is CL alpha T. Okay. Now, this Cm naught W will have two components, right. One is Cm AC W, what is given here actually, okay, plus CL naught W. So, this is actually this quantity is that. And I will say CL naught W into this quantity is okay. So, this let us try to expand this. Okay. So, okay. So, I am setting this alpha to 0 and that is CL naught W, and that will give you okay. So, let us try to mark the answers that we are getting. When we set delta E to 0, and alpha is also 0, and this CLT is 0, right. When this is the condition, when delta is 0, alpha is 0, what we have said is that lift produced at the tail is 0, right. So, this CLT is 0, and what you get is this. Right. AT is not 0. So, you can set this to 0 and get what IT is. All right. We will stop here actually, we will stop here.